We just saw the core in its entire length. Here's the upper segment again, which includes the present-day surface of the seafloor. And now we will find out how we can actually acquire quantitative climate information. I had already mentioned that there are microscopic organisms that live in the water and that sink to the ocean floor when they die. These organisms produce shells consisting of calcium carbonate. This is an example of a foraminifera, a chambered microscopic organism. Now this replica is greatly magnified. In reality, the diameter along this axis is about 0.5 millimeter. The interesting thing is that the calcium carbonate in the shells contains oxygen. And oxygen occurs in two isotopes, a light isotope 16O and a heavy isotope 18O. And we can use this to reconstruct the amount of ice that covered the land in the geological history. And this works as follows. The graphic again shows a section of the ocean. Seawater, H2O, contains oxygen too. Therefore, the ocean contains both light and heavy isotopes. If, as shown in the graphic, a glacial period occurs and large masses of ice cover the land, it is the light isotope that is preferentially transferred from the water into the ice. But the opposite also applies. The heavy isotope, the 18O, preferentially remains in the seawater. We can measure the ratio of 16O to 18O and quantitatively reconstruct how much ice covered the land. And we will look at this now. We have scanned the entire length of the core that we have just seen in the core repository with a color scanner in order to fully represent the information. This can be seen here. The horizontal axis is the depth along the core. The left side is the sediment surface and the right side is the sediment at a depth of about 11 meters, which is roughly 600,000 years old. The entire core is compressed here so that it fits into the graphic and you can still see something. You can see a series of light and dark layers. The dark layers represent glacial periods, and you can see that there are several glacial periods with intervening interglacial periods. The time span between these glacial periods is approximately 100,000 years. We've just learned that we can reconstruct the ice volume from oxygen isotope ratios that we measure in the foraminifera shells. And we will take a closer look at this now. The curve being drawn from the right shows us how much ice there was. The scale is such that the curve moves towards the lower edge of the image when little ice covered the continents. When the curve moves towards the upper edge of the image, a lot of ice covered the continents. Therefore, we can clearly observe the transition between interglacial and glacial periods. These glacial cycles are typical of the geological epoch of the Pleistocene. The glacial cycles we've seen are also accompanied by fluctuations in global average temperature. We know that global average temperature at the peak of the last glaciation was approximately 5 to 8 degrees Celsius below the pre-industrial value. After having looked at the fluctuations in ice volume and temperature, we'll now examine what causes glacial periods and the possible connection to atmospheric CO2 concentration. For this purpose, we'll look at a completely different climate archive, namely ice cores. The principle is similar to that of the ocean cores, which we have already addressed. However, it is the existing continental ice sheets that are sampled in this case. The fantastic thing about the Antarctic is that air bubbles are trapped in the ice. These bubbles contain fossil air, which can then be sampled, providing actual readings of the atmospheric composition of the past. We'll see this in this graphic. The horizontal axis does not represent the depth, as in the previous graph, but rather time, the geological age. Here we see the concentration of atmospheric CO2 in the last 600,000 years, approximately. The top graph is the one we've already seen and shows ice volume. The difference is that this is not based on a single record. Rather, as in the case of many other measurements in climate research, it comprises numerous oxygen isotope records from the various oceans in order to achieve as consistent a picture of the average isotopic compositions of the oceans as possible. At first glance, you can now see that whenever there is a glacial period, the atmospheric CO2 content is significantly low. If we look at the transition from the last glacial period to the current interglacial period in the Holocene, the difference is approximately 80 ppm. Thus, we are now able to deduce several things from studying these paleoclimate archives. Firstly, there have been transitions from glacial to interglacial periods every 100,000 years approximately. We can reconstruct these quantitatively, and we can also see that interglacial periods are accompanied by a higher atmospheric CO2 content. And if we look at the most recent CO2 history, namely that caused by humankind, which you can also see in the graphic here, it becomes immediately apparent that the natural fluctuations in atmospheric CO2 concentration were significantly smaller than the concentration of the atmospheric CO2 content today.